Hello students, today we are going to learn about the topic of PN junction and the biasing of it. It's a very important part of electronic devices. Okay, so the applicable streams are electronics and communications. Right, so in the last video we have seen about the extrinsic semiconductors, which are nothing but there are two types of extrinsic semiconductors. One is a p-type semiconductor and the other one is a n-type semiconductor. Now what we try to do in PN junction is that we try to merge a p-type and n-type semiconductors. So when we have generally a p-type semiconductor, we know in the case of a p-type, the majority charge carriers are holes and minority carriers are electrons, and we are going to have a representation of an acceptor ions, which are going to create holes. So here, with each and every acceptor ion, we generally represent a hole. This is how we represent a p-type semiconductor. And similarly, an n-type semiconductor can be represented. We know in the case of an n-type semiconductor, electrons are going to be the majority carriers and holes are going to be minority carriers. So we represent an n-type semiconductor which is having the majority as a electrons and minority as holes, and of course we represent the donor ions, and we know the donor ions are positive ions from what we have learned in the last video. So these are nothing but the donor ions. With each and every donor ion, we represent some electrons, so that to give an understanding that on full dopant ionization, each and every donor atom is going to donate an electron. So here you are going to have a majority as holes and minority as electrons. Those minority electrons, let us represent. Okay, these are some holes and electrons that are generated because of breakage of the covalent bonds. And so, because we already know that if you want to generate minority carriers inside a particular material, then definitely it is going to happen only because of the breakage of the covalent bonds. Whereas the majority carriers, the source is nothing but the dopants that we are doping. Similarly here also, we will have some holes which are minority carriers and also the electrons, because whenever the holes are generated, they will be generated in pair of electron and hole. So this is your p-type semiconductor, this is your n-type semiconductor. Now we are trying to merge both of them. Now this is going to be very interesting. What is going to happen upon merging a p-type and n-type semiconductors? So to the left side I am drawing a p-type, and to the right side I am drawing n-type. So upon merging the p-type and the n-type regions, so the PN which is formed, here there is a junction between that of P and N, which we call as the junction. With the center of the PN junction. Okay, this is nothing but the center of the PN junction where there is a merging of the p-type and n-type regions. Now it is very interesting now, because one region is going to be completely different to that of the other region. One region is going to have holes as the majority charge carriers, and the other region is going to have electrons as the majority carriers. So we know that whenever there is a high concentration of carriers at one end and a low concentration at the other end, what is going to happen? It's a very natural process that whenever there is a high concentration at one end and a low concentration at the other end, there is a process of diffusion which is going to happen, moving from high concentration region to the top a low concentration region. So this is a very natural process, because whenever you have a high concentration of something and a low concentration of the same thing, then it means that it will try to move from high concentration to low concentration region. A p-type region has holes as the majority carriers, and n-type region has holes as the minority carriers. So the holes which are present in majority carriers here, they try to move into the n region because of the process of diffusion. And similarly, the electrons which are present as majority carriers in the n region, they try to move into the p region because electrons are the minority carriers in the p region. So holes try to move into the n region, and electrons, these are the holes which are moving into the n region, and the electrons try to move into the p region. So what happens is that electron, hole, they try to move in the opposite direction. So when electrons and holes move in opposite direction, then there is a possibility of something called as recombination. So recombination happens, okay, when they try to move in the opposite direction, and there is a possibility that they are going to recombine with each other, provided the momentum values of electrons and holes are same. So the electrons and holes which are moving in the opposite direction, they try to recombine. So when they move in the opposite direction, they are going to recombine. So when they recombine, you can see no electron and hole in that particular region. So you can see that the electron and hole are going to miss. Similarly, an electron which is present here and a hole which is present here, if they recombine, they will go missing, because when an electron recombines with a hole, there is a process of a formation of covalent bond. So it is not represented in a particular diagram. The electrons and holes and ions are represented in this particular diagram. So what is happening here? This particular ion which was associated with a hole, now the hole is absent. This ion which is associated with an electron, that is going to be absent now. So there are some charges which cannot move. Can these ions move? These ions cannot move at all. Now these ions which are present here, they are not without any charge carriers. So whenever there is a negative ion in one region and positive ion in the other region, then there is a formation of an electric field. Whenever the positive ions are in one region, the negative ions in the other region, then there is a formation of an electric field which is directed from positive towards the negative. Always the electric field is directed from positive charges towards the negative charges. So the direction of electric field is going to be something like this. Now you can see here that the electric field direction is going to be in this direction. Always from positive charges towards the negative charges. Now whenever there is an electric field, there is a force associated with it, because here we are talking about the electrons and holes which are moving. So when they are moving in a particular direction, there will also be a force because of this particular electric field. Now what will be the force on the holes? Force on the hole is going to be equal to the of plus Q into E, where plus Q is nothing but the charge of the hole. So you can see that the force on the hole is going to be in the same direction as that of the electric field. Force on the hole is going to be in the same direction as that of the electric field. So the force on the hole is going to be in this direction. Now what will be the force on the electron? Force on the electron will be in the opposite direction, because you have minus Q into E. So minus Q into the direction of electric field. So it is going to be minus E is going to be the direction of the force on electron. So the force on the electron is going to be in the opposite direction as to that of the electric field, and also the force on the hole. Force on the electric field will be in the opposite direction to the force on the hole, and also in the direction of opposite to the electric field. So this is going to be the force on the hole, and this is going to be the force on the electron because of the electric field. Because of the electric field. We know that the holes are trying to move into the N region because of diffusion. Electrons are moving into the P region also because of the same reason. Now you can see that now the force on the hole is going to be in the opposite direction to that of the process of diffusion. Diffusion tries to happen by moving into the N region, whereas the force on the holes is pushing the holes into the P region. So there are two forces which are acting on a particular hole in opposite direction. One because of diffusion. So diffusion is a natural process moving from high concentration to low concentration, which is going to happen. Now there is a second force which is trying to push a hole into the P region. So both are opposite. So when there are opposite forces, which are acting, then whatever force is going to be dominant, that is going to show on that particular hole. So here there is a force because of electric field, and there is a diffusion. Now initially, because the electric field is weaker, So when the electric field is weaker, definitely the force is going to be also weak. So in that case, the diffusion process is going to dominate over that of electric field. So what happens is that the holes try to move, and same goes with the electron. The electrons also try to move into the p region because the force because of the electric field is weaker. So what happens is that slowly more and more electrons and holes are going to recombine with each other as the force because of electric field is weaker and the diffusion process is going to happen. Now can you tell me till when this particular process of recombination is going to happen and the electric field is going to become stronger and stronger? So for example, now you can see that there are two columns of holes which are missing, two columns of electrons are missing. Now let us think that now the force generated because of the electric field, because you're going to have a set of ions here. There are 8 ions in the p region, there are 8 ions in the n region. So compared to 2 ions in each region, now 8 ions, the force because of the 8 ions is going to be stronger. The electric field because of this particular ions is going to be stronger because the field becomes stronger because of the number of ions that are present. Now let us take a condition that now the force because of this particular charges is very strong when compared to the process of diffusion that can happen. The force is stronger, okay, when compared to the diffusion that is happening. So if that is the case, what is going to happen? That the force on the hole which is in this particular direction because of electric field, that is going to dominate over the process of diffusion. Now the holes cannot move into the n region. Similarly, the electrons also cannot move into the p region for the same reason. Because now the electric field is strong that it is going to oppose the direction of movement of the holes and electrons because of the process of diffusion. There is a concentration gradient. Even now there is a concentration gradient. But the electric field force is strong to stop the process of diffusion. So for that particular reason, a particular region is formed which is going to be completely depleted of charge carriers. A particular region is formed which is completely depleted of charge carriers. That is what we call as a depletion region. We call as a depletion region, a region which is completely depleted of the charge carriers. So that is what we are going to call as a depletion region. So this is clear to us. So initially what is happening? There is electrons and holes which are present in n region, holes are present in the p region. So starting when they are combining the p type and n type regions, the electrons try to move into the p region and holes try to move into the n region. So because of the process of diffusion. Now because they are moving in the opposite direction, they are going to recombine, and therefore a particular region is going to start forming, which is what we call as a depletion region. And the depletion region is going to have ions which is creating the electric field. Initially because the electric field is weaker, so the diffusion process is going to happen, okay, more and more. But as the electric field becomes stronger and stronger because of the bigger depletion region, we are having a huge number of ions. Now the electric field is so strong that it can stop the process of diffusion. So therefore a particular region is formed which we call as a depletion region, and it is going to have a particular potential inside it which we call as a built-in potential. Okay, so a built-in potential, so a potential which is generated in the particular depletion region is what we call as a built-in potential, which we can also call as a contact potential. So this is the concept of how the PN junction is formed, okay, how the PN particular junction is formed on creation of depletion region. So there are two types of PN junctions that we generally discuss. Okay, there are two types of PN junctions that we generally discuss. One, what we call as a step graded PN junction, the other we call as a linearly graded PN junction. So the first one is a step graded PN junction, the second one is a linear graded PN junction. So the first one is going to be more important in the examination, therefore we are going to focus on the step graded PN junction. So in the case of a step graded PN junction, one region is going to have higher doping when compared to the other region. I think when we studied about the extrinsic semiconductors, we have seen that there are three types of doping that can happen, three levels of doping, right? So high level doping, moderate level doping, low level doping. Now we are seeing that one region is going to highly doped when compared to the other region. Okay, it can be either P plus N or Pn plus, indicating that one region is highly doped when compared to the other region. Okay, that is what we call as a step graded PN junction. That is what we call as a step graded PN junction, which we can also call as a abrupt junction. So we'll try to focus on this particular part. So let me try to draw how the step graded junction is going to look like. So here we consider a step graded PN junction which is having no bias. Okay, so you can see that a P region is highly doped when compared to the N region, which is very much obvious, right? So in a particular column you can see here 6 ions, whereas here you're going to have 4 ions. These ions are nothing but the dopants, right? So you're going to have more number of dopants in a particular region, which is P, when compared to the N. That is why I'm terming it as a P plus N junction, which we can call as a step graded junction or a abrupt junction. So now let me draw some minority carriers as well. There will be some minority carriers. So along with the minority carriers, we know that it is because of the creation of the, it is because of the breakage of the covalent bonds. So the number of electrons and number of holes generated because of the breakage of the covalent bond will be same. So that is why I am drawing the equal number of electrons and hole pairs. Whereas the other electrons that I am showing here are nothing but because of the dopants. And the minority carriers and the extra majority carriers that I am drawing is because of the breakage of the covalent bonds. So that is the case here. So now what can happen is that the same old story is going to repeat again, that there is a hole which is dominating in one particular region and it is going to be less in the other region. So they try to move from the high concentration area to the low concentration area. So holes try to move into the N region and the electrons try to move into the P region, and we know when they are moving in the opposite direction there is a process of recombination that is going to happen. So because of the recombination, now the electrons and holes are going to recombine with each other. So we can see here that an electron is going to combine only with a single hole. Okay, so now 4 electrons and 4 holes and 4 electrons are going to miss. Now if you want to have if we have a weaker field, then more process of diffusion is going to happen. So let me consider that there is a recombination of 12 electrons and holes. Now let us consider that the electric field is going to be so strong that it is going to stop the process of diffusion. What we can see here is that one region is going to be smaller when compared to the other region. In terms of the thickness that we can have, if I can draw it as the width, the depletion region width, W, the depletion region width is going to extend more into the lightly doped region, because when the recombination is going to happen, it is going to happen between a single electron and a single hole. Now there are huge number of holes which are present in a smaller region of P when compared to the N region, because we are talking about a P plus N junction. So the thickness of the width inside the P region is going to be less when compared to that of N. That is because always the depletion region is going to extend more into the lightly doped region. The depletion region extends more into the lightly doped region, which is a very, very important point. The depletion region extends more into lightly doped region. Right? I think that is clear. So the width of the depletion region is given by a very important formula. The W is equal to 2 epsilon by Q 1 by Na plus 1 by Nd multiplied by V naught, where epsilon is the permittivity of substrate. It can be silicon or germanium or any material that you are taking, and Q is nothing but the charge, Na is the acceptor concentration, Nd is the donor concentration, okay, and V naught is what we have discussed as the contact potential. So V naught is the contact potential. So if it is not visible, I will write it out. Right? So there is a formula for the contact potential also. V naught is equal to Vt ln of Na divided by Ni square. So Vt is the thermal voltage, Ni is the intrinsic carrier concentration. Both are very, very important formulas. Okay, the depletion width, W, and the built-in potential are going to be very important formulas. So W, the width of the depletion region, is given by square root of 2 epsilon by Q, 1 by Na plus 1 by Nd into V naught, where V naught is nothing but the contact potential that we have seen earlier. And both are very important formulas. Okay. So we can see here that the width of the depletion region can be divided into two parts. One is that is present inside the P region, the other which is present inside the N region. Right? So we can write the width of the depletion region is given by xp plus xn, where xp is nothing but width of the depletion region in the P side, and xn is the width of the depletion region in the N side. So the next important thing that we are going to do here is that we are going to draw the charge density region of depletion. So inside the depletion region, we are going to draw the charge density profile. And you can see here that inside the P region, if you are considering only the P region is going to be uniformly doped. And similarly, if you are only looking at the N region is also uniformly doped. So the number of ions which are present are also uniformly placed here inside the depletion region. So the charge density is also going to be uniformly, the charge density is going to be a constant inside the depletion region. Why is it negative? It is negative because you are talking about the negative ions. So hence the charge density is also going to be negative. Similarly here, if you see the number of charges are going to be less. So, but still it is positive. So we are going to draw a particular region which is also positive. Now if you see the height or the depth that I am drawing here is higher inside the P region when compared to the N region. The reason for this is very simple, because you are going to have the higher concentration. So to represent that, I am drawing with the greater depth or height. So the depth here indicating the doping level. Now the doping level of the P region is higher when compared to the N region, which is clearly visible by the doping level or the height or the depth of this particular profile. So I can write here this is equal to that of Q into ND, because I am talking about the donor. So the charge density is going to be QND. Here it is going to be Q into Na. Okay, if you want to draw it negative, so it is going to be minus Q into Na. And the width here, if I am starting from 0 at the center of the PN junction, so this direction it is going to be XP and this direction it is going to be XN. Now what you will observe is that that the area of this particular profile, the charge density profile, yes, one important point is that if you see here, the charge density here in this particular region, which is what we call as the bulk of the semiconductor, is going to be equal to 0. And similarly here also the charge density is going to be equal to 0. The reason is very simple, because with each and every ion we have a hole. So ion is negative here and hole is positive, so they are going to get compensated over there. The only problem is in the depletion region, which is uncompensated. Okay, in a particular region you're going to have only negative ions. In a particular region you have only positive ions. So here we don't have a compensated regions. Whereas in the bulk of the semiconductor, they're going to have a compensated region. So there is no charge density in this particular region. So the area of this particular region will be equal to the area in this particular region. The reason is very simple, because here the depth is more, the width is less. But here the depth is less, but the width is more. So you can see that when the depth is going to be higher, the width is going to be lesser. Similarly, when the width increases, I mean to say when the concentration is less, the width is going to increase. So you can see that the area, which is nothing but the multiplication of width multiplied by depth. So the area has to be equal. So A1 is equal to A2 is a very, very important formula. So therefore we can write the area here is nothing but XP into QNA. If I only take the magnitude, then XP into QNA is equal to XN into QND. Okay, if I'm only talking about the area or the magnitude of it, so I can write that XP QNA is equal to XN QND. Q gets cancelled. So we have a very important formula here. XP into NA is equal to XN into ND. A very, very important formula in the gate examination. XP into NA is equal to XN into ND. One more important formula is that we're going to discuss about the electric field profile, and we have to find the peak electric field. So here, this is nothing but the charge density profile, and we should have a electric field profile. So what is the relation between the charge density and electric field? If rho s is going to be the indication of the charge density and electric field is by E, then electric field is given by equal to the of minus 1 by epsilon with an integral of rho s. This is the formula for the electric field. So electric field is basically the area or the integration of rho s ds multiplied by 1 by epsilon, where epsilon is once again the permittivity of a particular substrate. So we can rub this one. So now I already know the profile of my charge density. So this is my profile of the charge density. What I want here is the profile of the electric field. So the profile of an electric field in a way is nothing but the integration of this one. So when I integrate here, the profile is going to be something like this. So the electric field which is maximum is going to be somewhere here. I'm talking about the magnitude, okay? So the magnitude of the electric field is nothing but if you are integrating from this particular point to this particular point, you are reaching the maximum electric field. So when you are integrating from this particular point to this particular point, it is nothing but finding the area from this point to this particular point. Now what is the area here? So we know that it is nothing but 1 by epsilon into integral of rho s ds. So when you integrate from xp to 0, then you are going to have 1 by epsilon into q na multiplied by xp. So here I am only talking about the magnitude, right? So the magnitude of the electric field is going to be equal to the of q into na into xp divided by epsilon. Because the xp into na is equal to xn into nd, I can write this is equal to the of 1 by epsilon q into nd into xn. Okay, if it is not visible, I will write it here. So the peak electric field is given by the formula 1 by epsilon q na into xp, which is equal to the of 1 by epsilon q into nd into x. This is the formula for the magnitude of the peak electric field. So we have discussed about how a BN junction is formed, how a depletion region is formed, and we have also seen some important formulas of width of the depletion region, which is a very important formula. And apart from that, we have seen about the contact potential, and we have also seen some important relations like peak electric field. Now what I want to do is that I want to solve some gate problems on this particular concept. So let us solve some gate problems on what we have seen till now. So the question 1 is that first of all the doping levels are given. So this is the data which is given in the question itself. Now what we have to find is that the built-in potential and the width of the depletion region. So options are 0.7 volts, 1 into 10 power minus 4 centimeters, 0.86 volts, 1 into 10 power minus 4 centimeters. Right? So we have to find the values of the contact potential and the width of the depletion region. So you can pause the video and try to solve the problem. Let us look at the solution. So what is the formula for the width of the depletion, the built-in potential? V0 is given by Vt ln of natural logarithm. Ln is nothing but natural logarithm. Na multiplied by Nd divided by Ni square. So which is equal to the top. 26 millivolts can be written as 0.026 into ln of NaNd, which is 5 into 10 power 34 divided by 2.25 into 10 power 20. You can calculate this particular value. So the value will approximately be equal to the of 0.86. So we can eliminate two options, option A and option C. See, what we can see here is that you have to find the value of W, which is equal to the of square root of 2 epsilon by Q, 1 by Na plus 1 by Nd multiplied by V0. So what is there in our data is that Na value is going to be much higher when compared to the value of Nd. Yes or no? Na is going to be 5 into 10 power 18, Nd is 1 into 10 power 16. So Na is going to be much higher when compared to the value of Nd, and 1 by Na is going to be much lesser when compared to the value of 1 by Nd. Right? So what I can do, I can eliminate the value of 1 by Na because 1 by Nd is much higher value, so I can only consider that one. So let me do that. Let me apply the formula. So the value is going to be something like 3.27 into 10 power minus 5, and of course we'll get the answer in centimeters because each and every value is expressed in terms of centimeters. So therefore the answer will also be in terms of centimeters. So 3.3 into 10 power minus 5 centimeters and 0.86. So option D has to be the right answer. Let's see the next problem. Question number 2. So we have to find the value of the peak electric field. Basically, you have to find the value of the peak electric field. What is given here? The doping concentration of the N region is given. So N region is slightly doped when compared to the P region. That is visible here. So Nd is given as 10 power 16 per centimeter cube. The width inside the N region is given as equal to 0.2 micrometers. Okay, the width inside the N region is given as 0.2 micrometers, and the permittivity of the silicon is also mentioned in the question. So what we have to find is the peak electric field. We have learned the formula for the peak electric field, which is nothing but Q into NdXn divided by epsilon. So we can directly apply this one. So it is equal to 1.6 into 10 power minus 19 into Nd, which is 10 power 16, multiplied by Xn, which is 0.2 into 10 power minus 4 centimeters. I want to write in terms of centimeters, so it is going to be 10 power minus 4 centimeters divided by epsilon, which is 1.044 into 10 power minus 12. Okay, you can just simplify it using the calculator. It's equal to 0.306 into 10 power 5 volts per centimeter. The answer you're getting is 0.306 into 10 power 5 volts per centimeter. See, in the question what is asked here, kilovolts per centimeter. So I want to write in terms of kilo. So if I write in terms of kilo, it is going to be 0.306 into 10 square kilovolts per centimeter, which I can write it as 30.6 kilovolts per centimeter. So you have to write the answer, the fill in the blank, as 30.6. Okay, so 30.6 is the right answer. So till now we have seen about a particular PN junction, which is a step-graded PN junction. Now we are going to bias it. Okay, we have seen about a abrupt junction. Now we are going to bias it. Till now we didn't bias it. Still we have seen some important parameters like width of the depletion region. We have also seen about the built-in potential or contact potential. Okay, and peak electric field. So these are some important formulas that we have learned till now. Now we are going to extend it by applying the concept of biasing. So whenever you are applying some energy, which is nothing but an electrical energy in particular, because your diode is nothing but an electronic device. So we generally supply some or provide some electrical energy. So we can apply the energy because it's a directional device. It's not going to be bidirectional, it's going to be unidirectional device. So its performance, when you're applying potential difference in one direction, is going to be different to the top if you're applying the potential difference to the other direction. So when you are applying the biasing, when you are learning the concept of biasing, what we're trying to do here is that we're trying to apply the potential in both directions, and we are going to learn the characteristic in both the directions. So there are two types of biasing that we're going to learn. One is what we call as a forward bias, the other is a reverse bias. So it's very important to learn why we apply this particular concept, because for the working of a particular any device we apply some potential. So what happens if you are applying potential in a particular direction is what we are going to learn as a forward bias and reverse bias. So these are the two types of bias that we are learning. First we will emphasize on the forward bias. Okay, so we'll learn about the forward bias. So for that I am once again going to draw a depletion region and the bulk region, right? So inside the depletion region probably something like this is there. So this depletion region is already formed. So I'm just roughly drawing the depletion region here. So here you can see that you are having a PN junction where the depletion region is already formed, right? So we know the formula for the width of the depletion region, contact potential, etc. First thing that I'm trying to do here is that I want to apply the forward bias, which is nothing but applying the positive terminal of the battery to the P region and the negative terminal of the battery to the N region. If you apply the positive terminal of the battery to the P region and the negative terminal to the N region, the bias that is formed is nothing but the forward bias. Okay, so if you want, you can keep a resistor which we call as a current limiting resistor. Now what is going to happen as a consequence of this one? You have to realize that when we have discussed about the depletion region, that there is an electric field which is formed in this particular PN junction. Okay, in the depletion region itself, there is a electric field which is formed, and the direction of electric field is going to be something like this. Always from the positive ions towards the negative ions. This is nothing but the built-in electric field. Right? Now, whenever you are applying the electric field where the positive terminal of the battery is connected to P side and negative terminal to the N side, now the direction of the field is going to be in this direction. This is nothing but the electric field because you are applying positive here and negative here. So the direction is going to be from positive to negative. So therefore, the external electric field or the applied electric field will be in this particular direction. So the built-in electric field and the applied field both are in the opposite direction. The built-in field and the applied field both are in the opposite direction. So when both are in opposite direction, what is going to happen? So initially you don't have this one, you only have this one, correct? So when you have an electric field, what was the major problem that was created? The major problem that was created is that this electric field is stopping the process of diffusion, yes or no? This particular electric field which is generated is basically stopping the flow of the majority charge carriers because of diffusion. Now when you are applying the field which is going to be in the opposite direction to the built-in field, now it means that this field, the applied field, is going to make the built-in field weaker and weaker. It will make the built-in field weaker and weaker. So when the field is becoming weaker, when this field which was stopping the process of diffusion is becoming weaker, now what happens? Slowly the process of diffusion is going to happen. It means that now the electrons which are present in the N region and the holes which are present in the P region, now they can freely move. They can freely move. That is nothing but the concept of the forward bias. Basically, forward bias is applied so that we can have the current inside the particular material. So now the holes move into the P region, the holes try to move into the P region, and the electrons try to move. I mean to say, the holes try to move into the N region by crossing the depletion region, and the electrons try to move into the P region by crossing the depletion region. Okay, so when they are moving, so there is a hole current in this direction, there is an electron current in this particular direction. So the total current is going to flow in this particular direction. This is going to be the direction of the total current. This is your forward bias. So how the current is possible here? Because you have a short circuit, you have a battery, proper battery. Now there are the holes and electrons which are going to move by removing the influence of the electric field, the built-in electric field. So you have to understand when you learn about the forward bias is that the purpose of applying the forward bias is to make this particular built-in field equal to 0. The effect of the built-in field is reduced to 0 by applying the forward bias. See, here the forward bias is not applied so that we can have a current. Okay, then that particular current is nothing but a drift current. We have learned already, right? Whenever you are having an electric field, the current produced is nothing but drift current. But here, the current is going to be diffusion current because the purpose of applying the electric field is to compensate the built-in electric field. The purpose of applying the forward bias is to compensate the built-in electric field so that when you remove the built-in electric field, automatically because of the process of diffusion, the current is going to happen. Right? So that is why the forward current is what we call as a diffusion current. The forward current is what we call as a diffusion current. So when we learn about the VI characteristics, we'll try to emphasize more on what will be the relation between the applied voltage, the drop across it, and the current which is flowing in this particular region. So we have learned about the forward bias. So the purpose is to make the built-in electric field as less as possible so that we can have a current in a particular device. So the current is possible, a significant amount of current is possible in the forward bias. Right? So that is what we have learned in the forward bias. Now let us learn about the reverse bias. Right? So here in the case of the reverse bias, there is no requirement of the resistor because the current which is going to flow as a consequence is going to be very less. So now, if you don't apply any reverse bias, it means in the no bias condition, you are already having an electric field, right? In the no bias condition, we already have an electric field. And the electric field is from the positive ions towards the negative ions. This is nothing but the built-in electric field. Now, we are applying a particular voltage in such a way that negative terminal of the battery is connected to P side and the positive terminal of the battery is connected to the N side. negative terminal of the battery is connected to the P side and positive terminal of the battery is connected to the N side. So by doing that, it means that negative is applied here, positive is applied here. Therefore, the applied field direction is going to be opposite to the of the forward bias. The applied field direction is going to be in the opposite direction to the of the forward bias. So what is happening here? The applied field, because of the battery, is going to be in the same direction as that of the built-in electric field, which is opposite to the of what we have learned in the forward bias. We are just changing the polarity, right? So now the field direction is going to be in the same direction as it of the built-in electric field. So when that happens, when the direction of the electric field which is applied is going to be in the same direction as the built-in electric field, now the strength of the field is going to be very, very high. So when the strength of the field is going to be high, what is going to happen? So we know that the strengthened field is going to be very strong. The strengthened field is going to be very, very strong. Now we know the force on the electrons and the force on the hole. If you have an electric field in this direction, force on the electron is going to be in the opposite direction. Force on the hole is going to be in the same direction as that of electric field. So holes which are present in the vicinity are going to be pushed into the P region, and the electrons which are present in the vicinity, they are going to move into the N region. You have to understand that the field is going to be much stronger when compared to the built-in electric field. Now because of that, these holes which are present here, they will be pushed into the P region. Why? Because there is a force on the hole which is in this direction, right? Now therefore, the holes are trying to move into the bulk of the semiconductor of P region. Here the electrons also try to move into the bulk of the semiconductor of the N region. More the amount of electric field applied, more the number of electron holes which are moving into the P region, and more electrons are going to move into the N region over here. Now what happens if the holes are vacating here? The width of the depletion region is going to be higher and higher. The width of the depletion region is going to become stronger, higher and higher. So width of the depletion region, which was proportional to the square root of V naught in the previous case. If you remember, we have a formula W is equal to square root of 2 epsilon by Q into 1 by Na plus 1 by Nt into V naught. So width of the depletion region is proportional to the drop of the voltage, which was built-in voltage if you don't apply any bias. Now the width of the depletion region is going to increase. That width of the depletion region is now going to be V naught plus Vr. V naught is nothing but the built-in value. Now you are strengthening it by applying the bias, which is nothing but a reverse bias. We call it as a reverse bias. Now based on this particular concept, a problem has been asked in GATE. So let us try to solve that particular problem. So given a PN junction, it's a P plus N junction. V naught, the built-in potential, is going to be 0.8 volts. And the width of the depletion region in the P side, okay, so the reverse bias that is applied is given as equal to 1.2 volts, and the width of the depletion region correspondingly is given as 2 micrometers. Now when the reverse bias of 7.2 volts is applied, what is going to be the width of the depletion region? This is the question. Okay, it is based on the same concept, right? So the width of the depletion region is going to increase according to the reverse bias that you are applying. So initially when the reverse bias voltage is going to be 1.2 volts, then the width of the depletion region is 2 micrometers. And when the reverse bias of 7.2 volts is applied, what is the width of the depletion region? It's very simple, right? You can directly solve it by W2 by W1 is going to be square root of V naught plus VR2 divided by V naught plus VR1. So this is equal to the top. So 0.8 plus 7.2 is going to be 8 divided by 0.8 plus 1.2 is going to be 2, which is equal to the top square root of 4, right, which is nothing but 2. So W2 is nothing but 2 times the top of W1. So W2 is going to be equal to 4 micrometers. The answer is that W2 is going to be 4 micrometers. Right. So what is happening here? when you are applying the reverse bias voltage, now because of the application of the reverse bias voltage, the depletion region width is going to increase. And there is an accumulation of holes which is happening in the P region, and there is an accumulation of electrons which is happening in the N region. So whenever there is an accumulation of charge carriers that is happening, it is leading to the development of potential. Positive charge here and negative charge here, because electrons are negative charges, right? So electrons are depositing here and holes are getting deposited here. So it is leading to the development of potential difference. So therefore, whatever voltage that you are applying is going to lead to the potential difference, and there is no current which is going to flow except that the minority carriers are present. Because we know that force on the electron is going to be in this direction, right? And force on the hole is in this direction. So whatever holes which are present here, they can move in this direction. And whatever electrons which are present, they are going to move in this direction. So holes move in this direction, electrons move in this direction. So there is no problem with the minority carriers. But we know that minority carriers are far lesser when compared to majority carriers. Minority carriers can move, but majority charge carriers are getting accumulated here. So the amount of current is going to be ideally zero, and practically there is going to be very less amount of current because of the minority carriers which are present. So the current because of the minority carriers is what we call as a leakage current. Okay, so I'll tell you why it is called as a leakage current. So first let us try to compare the forward bias and the reverse bias. In the case of forward bias, it was leading to a particular current. Okay, and in the case of a reverse bias, it is leading to the accumulation of voltage, and therefore the current is becoming equal to zero. Now we can compare this one with the switching on and switching off. So whenever we are switching on, then the current is going to flow. Whenever there is switching off, the current is going to stop. So forward bias is something that we can relate with the of switching on, and reverse bias is something that we can relate with the of switching off. But what we actually require in the case of switching off is that we require that the amount of current should be equal to zero, because when you switch off, there should not be any current. But here there is some amount of current which is flowing because of the minority carriers. That is why we call it as a leakage current. Okay, and this is not a desirable current, this is an undesirable current, because whenever you are applying a reverse bias, it has to lead to the amount of current equal to zero. Whenever you have a forward bias, it is nothing but switching on, and you want the current to flow. That is okay. But in the case of a reverse bias, basically it is not going to. Of course, in the case of an ideal case, it is not going to have any current. That is what we desire. But practically, there will be some amount of current. That is nothing but the reverse current, or what we call as a leakage current. And that is going to create a problem when we see the BJT, the Bipolar Junction Transistor, where we will discuss a very big problem which we call as a thermal runaway. It's a very big problem in the case of BJTs that won't happen in the case of the field effect transistors. Okay, I hope we understood about the concepts of how the PN junction is formed, width of the depletion region, very important formula, contact potential, very important formula, peak electric field, once again a very important formula, as well as we have seen the forward biasing and reverse biasing, which is a very important topic for electronic devices. So that is what from our side for this particular day. Okay, so enjoy the classes. Okay, keep watching. All the very best, and thank you.